or formulas from the data packet. This one is Snell's law. Usually it's written this way these are the indices of refraction, right? So the index of refraction, this formula is not in the data packet as far as I can tell. The index of refraction is the speed of light divided by the velocity in the medium. Okay, so remember the index of refraction is a number bigger than 1 because when light enters even air, it slows down a little bit, right? So the speed of light in the vacuum, this is our 3.00 times 10 to the 8th meters per second, right? And then this is whatever it is, like in water, it's something like 2.26 times 10 to the 8th meters per second or something like that. I can't remember exactly, right? And so n's are bigger than 1. N's are bigger than or equal to 1. The index of refraction of a vacuum, okay, is 1. The n is 1, okay? Because it goes the speed of light. It'd be the speed of light over the speed of light, right? Okay. Typically, you write Snell's law this way: n1 sine theta 1 equals n2 sine theta 2, which you would get if you cross-multiplied this expression. IB writes it this way because I think because they want to do the whole thing with the velocity, right? Okay. Notice that that these little subscripts reverse, right? So n1, n2, sine theta 2, sine theta 1, v2, v1, right? And this would be the velocity in the medium. So these are velocities, right? This is the angle of refraction. So remember, angle of refraction is this guy. Okay. And they always like to catch you on that, right? So this is our incident angle, so maybe that's theta 1. And if this is a slower medium like water, it'll bend like that, and this is theta 2, right? And then we've got the index of refraction 1 here, the index of refraction 2, right? An index of refraction is kind of a backwards thing. The bigger it is, the slower the more the light refracts, right? The more the light slows down. The wavelength here, we've got a wavelength 1, right, and a wavelength 2. This wavelength is shorter because the velocity is slower, right? So that it's like cars on a freeway, they pile up, right? And then the angles work like this too. And then we also have a velocity in this medium and a velocity in that medium, okay? And then this is a formula for Young's double slit. Okay, so if I've got like a barrier like this, and I've got 2 slits, and then I've got incident waves. Let's change the color to red. I've got like incident waves like this. This is like a beam of laser light, and these are the crests, and these are the troughs in between, right? Remember that the light is going to spread out from these things, right? It'll diffract, and it'll overlap on a distant screen. It'll overlap on a distant screen. So here's a screen back here, and you'll get a bright spot, and a bright spot, and a bright spot. And the bright spots are places where there's constructive interference, right, where the path length is an integer number of wavelengths. So this is 0 wavelengths, closer to this one than this one. It's the same distance from this one, right? This is 1 wavelength closer to this slit than this slit. This is 2 wavelengths, so 1 wavelength, 2 wavelengths, right? 3 wavelengths, et cetera, right? So you get a central bright spot, and then you'll get these other little bright spots. They get dimmer and dimmer as they go out, like that, right? And then if we want to use this formula there, okay, let's get another color. D is this distance. So this is D, how far away the screen is. Okay, little d is this distance, how far apart the slits are separated. Okay, S is this distance here, the distance between one and the other one. Because my drawing is greatly exaggerated, D looks about the same size as S, but D is really quite small, fraction of a millimeter, right? And this is our S, right? So they're saying that the distance that these dots are separated is the wavelength of light times the distance to the screen over the distance separating the slits, right? It comes from a simple proportion that you can set up, and that is that lambda is to D. So if the two small things, wavelength and the slit separation, lambda is smaller than the slit separation, that equals S over D. And you can show a simple proportion. I'm not going to go into it right now. But if you want to solve this for S, obviously you just put the D up here, and you end up with that, right? And then this final one here, this is constructive interference and destructive interference. So if you've got a source and a spot, right, and you figure out the distance from here and the distance from there, right? If this is, say, 3 wavelengths, and this is 5 wavelengths, right, there's a difference in distance of 2 wavelengths, right? If it comes out even, if it's an even number of wavelengths, it's constructive interference. It's loud, right, or bright. This color of ink is making my eyes hurt. I can't look at it anymore, right? And then if you pick another spot, let's say we pick this spot here, right? And we are just making this up. Okay, let's imagine that we are 2 wavelengths from this guy, right? And 4.5 wavelengths. Even though that looks longer than this, right? Okay, well that's a difference in distance of 2.5 wavelengths. So this, we would expect this spot, if these are speakers, right, and they are in phase, that is, they go in and out in unison, right, and they are monochromatic or in the same frequency, right. This is true, right. So this would be a case if the difference in distance of 4.5 minus 2 wavelengths, right, is 2.5 wavelengths. If it's something like that, if it's a half a wavelength, 1.5 wavelengths, 2.5 wavelengths, right? These are destructive, right? So this would be quiet, or it would be dim. There we go, right? A lot of stuff in these equations. So there you go. Sorry about that.